Digital mammography equipment, design, use, and physics for mammographers. Let's take a look at how to optimize our equipment to produce quality 2D and 3D digital mammograms. This program is designed as a review for the mammographer, the professional radiographer, to analyze the design and use of digital X-ray equipment for mammography. We'll look at the basic components of the equipment and how they are utilized in creating quality mammographic images. The principles and physics of mammography remain the same, despite the different types of manufactured equipment available or modalities available in the market today. A thorough knowledge of the components of the equipment and how to optimize their use will result in quality mammograms. So let's begin to explore the equipment utilized to create 2D and 3D digital mammograms. Here we have both a picture of a dedicated mammographic unit and a line drawing. We'll try to use a number of visuals to be able to demonstrate the material contained in the presentation. Digital mammography. What do we really need to know? Although we produce images using an X-ray source, mammographic equipment differs greatly from the routine diagnostic equipment. We also know breasts are like snowflakes. No two are alike. Each patient is unique and different. Here we can see a categorization of the breast tissue from 10% of the women having an almost entirely fatty breast to 40% of the women having scattered areas of density, while 40% more of the women have very dense breasts and about 10% extremely dense breast tissue. In reality, the fatty breast and the extremely dense breasts have very similar tissues, fat and fibroglandular tissues, with about the same atomic number. Since the tissue is so similar, there's very little contrast, and this is what makes mammography difficult. To get the highest contrast and image resolution, we need to optimize each part of our equipment's use and do very, very good positioning. Most people believe that mammography is done just for cancer, and this is not true. A woman's breasts change over her entire lifetime, and there are many different types of pathologies that can be demonstrated mammographically. There is a trend that two-dimensional radiographs or traditional radiography is being replaced by three-dimensional radiography, which is basically tomosynthesis or a CT of the breast where you can look at individual slices of tissue. In digital mammography, there is image capture and image display. Each manufacturer uses unique components, and systems may differ even within the same manufacturer based on the configuration. The technologists work independently from the radiologist and often have different quality of display monitors in use. So we have to take a look at the quality of the radiologist monitor and the visual display and the quality that the equipment has for visual display for the technologist. The technologist display is not as good a quality as the radiologist, so the technologist must rely on exposure index numbers and other measurements that they can utilize to analyze their images prior to sending the image to the radiologist to be read. Mammography shares the same fundamental principles with radiography, but has its dedicated equipment and techniques to meet the unique challenges of breast imaging. For example, mammographic systems use X-ray beams of significantly lower energy than do standard X-ray equipment These low energy or low KeV beams have a kilovolt peak or the optimum penetration of between 20 and 35 kVp. This low energy allows an increase in difference in attenuation between normal and cancerous tissues and other pathology that would otherwise be too subtle for detection. Mammographic systems also use smaller focal spots and other measures to improve their spatial resolution for detecting very, very small microcalcifications. Digital images have the advantage that they can be enhanced and manipulated by a computer to extract the maximum amount of diagnostic information. Digital images can be stored, transferred, and copied without detriment and retrieved in a very efficient manner using computer mass data storage technique. They have the disadvantage of a limit to spatial resolution caused by the finite pixel size that creates the image. The term pixel stands for picture element, so it's the small picture element size that creates the spatial resolution. Resolution, contrast, choices of filter and anode combinations, all of these differ between the different manufacturers. But of all things, one remains the same. All mammography images must be displayed on a 5 megapixel monochrome monitor that has a cleared 510K filing with the FDA, which specifies that its use is intended specifically for mammography. The 5 megapixel monitor is for the radiologist, and these monitors not only have monochrome but color and go up to 12 or more megapixels. The higher the number of megapixels, the smaller the elements are that can be seen. Remember, the diagnosis is being made off of the radiologist's monitor and their visual acuity. As an example, a technologist may get a 2 megapixel monitor to judge the images, while an interpreting physician must, by FDA standards, have a monitor of greater or equal to 5 megapixels. Let's review some of the digital mammography applications. We start with real-time image display, then have post-acquisition image enhancement, image archiving and retrieval, and the ability to transmit the images simultaneously to several different monitors, which gives us teleradiology. The radiologist may also choose to post-process the energy in the image and have a dual energy subtraction to match to the image that was acquired. Some systems have the ability to use computer-aided image analysis and artificial intelligence analysis to help the radiologist in determining an interpretation. One of the greatest applications to come along in a time has been the 3D tomosynthesis. Nowhere else in medical imaging are technologists or mammographers faced with so many variables that will influence their ability to produce a quality image. These variables include size, shape, texture, mobility, and tenderness, as well as previous breast procedures. The breast may also have implants and a level of encapsulation from the implants, and there may be a difference in the implants due to their age and type. Also, a woman's breasts or a patient's breasts change during their entire lifetime, from birth until death. Usually, we're looking for breast cancer and other pathologies. Breast cancer can occur at any age, but is usually postmenopausal. The postmenopausal woman usually has fatty breasts as opposed to dense breasts that the patient would have in their youth. Although rare, men also get breast cancer. In 2020, an estimated 2,620 men will be diagnosed with breast cancer this year, and it is approximately 520 of those will die. There is a challenge in being able to do male mammography. Another significant challenge for the mammographer is the transgender patient. Transgender patients may be male or female and have additive or subtractive types of modifications to their body. This makes it very difficult for the mammographer. The changes in the body in the transgender patient make it difficult to analyze technique and position. Transgender individuals are increasingly referred for both screening and diagnostic breast imaging. It is important that the clinic environment is welcoming, and the medical staff utilize accepted terminology, and patients can designate their gender and personal history to ensure appropriate care. Hormone and surgical treatments used for transition by many transgender women and men may change the approach to imaging required to get a quality mammogram. Let's return to looking at the breast tissue and how to demonstrate this tissue with our mammographic systems. Based on the type of tissue that we're trying to analyze, we will modify our beam filtration or beam hardening to be able to demonstrate through the thick breast as opposed to the more contrasty fatty breast. When we increase the KVP, of course, we also increase the scatter radiation or shades of gray. The final product should have good contrast for breast tissue, and this includes being able to demonstrate morphology of a mass or distortion of normal breast tissue architecture, which indicates a pathology process. The mammograms must also have high spatial resolution or detail. This means that shape and spatial configuration of microcalcifications can be seen. We use low KEV to try to get high contrast because of the similarity of the tissue, but we also want to have low dose for the patient. This means that the mammographic unit is designed differently than a regular X-ray unit to enhance the ability to use the least amount of radiation to get the highest quality image. So let's look at a basic configuration of the X-ray component. We start with the angled tube head. The cathode would be placed over the chest wall, which is the thickest part of the breast, to exploit the anode heel effect, which has higher energy at the thickest part of the breast and better detail at the thinnest part of the breast. We also use the ALAR principle of a fixed focal to film or image receptor distance of 65 to 66 centimeters, which is about 27 inches, as opposed to the 40 or 44-inch SID that we utilize for routine radiography. This allows us to cut our mass and save significant amount of radiation to the patient. We also use a different target filter combination in the X-ray tube, different from the general radiography tube. For general use, we usually use a molybdenum and molybdenum filter and anode combination at approximately 25 kV. When we get dense breasts, we change to a moly-rhodium filter or a rhodium-rhodium anode and filter at 32 kVp. As we all know, the remnant radiation is made up of both scatter and photoelectric effect energies. And we'd like to get rid of the scatter energy because they provide no useful information. So we also use an anti-scatter grid in our mammographic system. We all know that with an X-ray tube, the smaller the focal spot size, the better the spatial resolution. In mammography, we use a 0.3 millimeter focal spot size normally, and can use a very fine focal spot size from 0.1 to 0.15 millimeters for fine focus. We do have a number of 2D planar units in use, but more and more we are going to 2D and 3D units, which incorporate the 2D planar and breast tomosynthesis for 3D imaging. As you know, in tomosynthesis or tomograms, the tube travels in an arc, and it allows us to take slices because the image receptor goes in a different direction. And it is the geometry of the arc and the motion that create the image slices. This means there are some very large differences between a fixed 2D unit and a unit that is capable of doing tomosynthesis mechanically. Exposure is dependent upon the thickness and the quality of the tissues being penetrated. In mammography, we want to decrease the thickness and density by compressing the breast. Breast compression allows us to use less radiation, and also we get better spatial resolution on the tissues that we do penetrate. A compressed breast does not allow the same amount of secondary and scatter radiation as there would be in an image of an uncompressed breast. Let's take a look at how compression actually impacts on the density of the tissue by creating less volume. Here we can see on the right, a compression paddle is compressing the breast. Compressing the breast gives us less tissue density, so less scatter radiation. At the same time, it allows the internal areas of interest to come closer to the image receptor, increasing their resolution. At the same time, we decrease the exposure to the patient. Now let's take a look at the different components of a full field digital unit and its operation. The operation is the same. The ACR positioning and labeling guidelines are the same. The compression is the same. There is no photocell to position. It has autocell. And there are no cassettes to load into the bucky. And there's no leaving the room. So a full field digital unit does differ from the traditional film screen unit. Looks like a little quantum model has been cleared up there. Let's talk about optimum photon energy and the clarity and spatial resolution of the breast and digital need for signal. Remember, with signal starvation, we get quantum model, and we get a beautiful picture, but more exposure if we overexpose. The challenge in mammography is to optimize the energy of the beam so that we get the best exposure or the best quality image with the least amount of exposure. Let's take a look at the energy required to do a thick breast as opposed to the energy required to penetrate a thin breast. And you'll see that the 15 keV is much less than the 30 keV. For the higher keV, we must use more penetration, or kVp, a higher kVp, which means more secondary and scatter radiation. The selection of the appropriate combination of target filter materials is a non-trivial matter in mammographic tube design. When moly or rhodium is used as the target material, because of the abundant characteristic X-rays produced in the spectrum, the K-edge of the added filter needs to be slightly above the energies of those characteristic X-rays so as not to absorb the useful photons. If molybdenum is used as the target material, both molybdenum and rhodium can be used as filter materials. If the rhodium is used as a target material, then the rhodium itself is an acceptable filter material, but molybdenum would not be a good candidate because its K-edge is lower than the energies of the characteristic X-rays produced by rhodium. Here we see the filter wheel that is utilized in a mammography system so that we can select the different types of filters. You can see how using the filter wheel we're able to select the type of filter we want to use in conjunction with our anode. The machine automatically chooses a filter depending on the breast thickness and density. With rhodium combination and tungsten, we are utilizing a filter combination for a dense breast, which would be more than 6 centimeters as compared to the usual 4 centimeters. So we're going to have 20% more glandular tissue, and we need more penetration. Since the very dense breast only makes up a small percentage, maybe 10% of the breast, it is highly recommended to use a combination of moly and rhodium, or rhodium and rhodium, as your filter and anode combination. The target filter combinations of tungsten rhodium and tungsten silver are used mostly for tomosynthesis acquisition, a mode of multi-view acquisition for producing a 3D-like image. The moly rhodium or rhodium-rhodium combination is used for general 2D planar radiography. Here we get an idea of the tungsten spectrum that is utilized for tomosynthesis. You can compare the tungsten with the tungsten and rhodium combination. For a breast thickness of 6 cms with a fibrofatty nature, the tungsten-rhodium combination delivers a high performance in terms of image quality at a lower dose. And here we can see the comparison of the tungsten rhodium with tungsten silver for the signal-to-noise ratio that we get with this combination. Remember, the signal-to-noise ratio is how much mass that we are using to produce the digital image. Obviously, we don't want to have too much mass because we're overexposing the patient, but we don't want starvation of the mass where we end up with quantum model. Here we're looking at the comparison of a moly-moly target and a moly-rhodium target. For mammography, we usually have a molybdenum target with a molybdenum filter, but this does not give high enough energies for larger breast. So rhodium has a higher K-edge at 23.3 keV, and we can use molybdenum target and a rhodium filter to increase the amount of X-rays with energies in the range of 20 to 23.3 keV. Rhodium has characteristic X-rays that are 20.2 to 22.7 keV. When we use this as a target, this produces a beam with a mean energy that is higher than the moly-moly and for molyrhodium. Finally, we see the tungsten target and the rhodium filter. This is used for tomosynthesis. Beam quality matters. Also, we use the beam quality to use the type of combination that will provide the best information for the values of interest that we're looking for. What does that mean? Basically, we're going to use a combination that will show microcalcifications. We're going to use a combination that will show masses. We will use a combination for dense breasts, and we'll use a combination for tomosynthesis. All of this is chosen by the mammographer. Now let's take a look at the mammographic X-ray tube. The X-ray tube is different than the tube that is used for a regular X-ray system. The first difference is the target, and as we've been discussing, there are different types of targets that can be chosen from. The next is the glass housing. The glass housing has a window or a beryllium window to allow the softer rays to go through. Otherwise, the glass would block those rays. And there is a change of the anode tilt dependent upon the degree that the tube is going to be tilted. The idea being that we're going to have the divergency of the beam such that the geometry is such that the CR goes through the middle of the breast, and the divergent side on the cathode does not have radiation going beyond the chest wall. As we know, the anode heel effect allows a more powerful portion of the beam to go up against the chest wall, and the more clarity or better resolution towards the side of the nipple. The cathode has smaller focal spots compared to a diagnostic X-ray tube. We have two focal spot sizes, usually a 0.3 and 0.1 millimeter are typical values for this focal spot sizes. The smaller the focal spot size, the better the resolution. Let's take a look at the difference between the actual focal spot and the projected focal spot size. Notice the difference in the resolution starting from the cathode side, getting smaller, or the size being smaller as we're going to the anode side. Therefore, we're getting more detail in the smaller portions of the breast and more intensity of the beam at the cathode or the chest wall side. As you can see, the mammography equipment, including the tube, is specifically designed to take advantage of the physics and the geometry to create the best quality images possible with the least amount of exposure to the patient. To the left, we can see the tube, part, receptor alignment. Let's reflect on the tube angle, the filtration, collimation, the compression device, of course the shape of the breast, and the image receptor, and the divergency of the beam. It's quite obvious that a mammographic system is designed for one purpose and one purpose only, quite different from the standard radiography room. We'll begin by looking at the intensity of the beam and reasoning that that is why the base of the breast is always, or the chest wall, placed against the cathode side of the tube for positioning. The reasoning behind this is that the photons have further to travel to exit the anode, and the photons have less material to travel through to exit the anode. The photo shows the standard mammographic unit, and the diagram shows the interior or the housing of the X-ray tube itself. Here we take a peek underneath the trim covers of the equipment to notice that in the housing we have the X-ray tube. It has an exit port, and we also have the angulation of the X-ray tube in relationship to the breast. Now let's compare the tube with a regular X-ray tube, and here we see a regular X-ray tube with the emission angles of the X-ray beam. So let's compare the geometry of the X-ray emission to the geometry of the human breast. Traditional use of the X-ray tube without an angle does not give us any benefit for imaging the breast. When the X-ray beam exits the X-ray tube, we want the beam to be collimated or restricted, and we have a collimator set of blades to do just that. Collimation of the beam eliminates all the unwanted and unnecessary radiation to the target area and cuts down on the secondary and scatter radiation. Using collimation reduces the dose to the patient, X-ray dose, and it also gives us more image contrast. This graphic demonstrates two types of automatic exposure control, the old AEC and the intelligent AEC that is being used more today. The intelligent AEC system is more accurate in the data it sends to the computer to control exposure. Understanding the X-ray tube positioning and angle will help you in positioning the patient. The two primary positions for mammography, of course, are the medium lateral oblique and the cranial caudal position. Prior to the remnant radiation coming in contact with the image receptor, we would like to clean up the beam and get rid of some of the secondary and scatter radiation. To do this, we use an anti-scatter grid. In positioning the patient, we also need to be able to position the equipment. Therefore, we have mechanical positioning of the different components within the system. Vendors look at the interaction with the mammographer with the system and how it can be positioned as a key in selling their product. This means that although the functionality is similar, each machine has its own idiosyncrasies in manipulating the mechanics of the system. Now we'd like to take a look at the different types of image receptors. We have an indirect and a direct receptor. Some people may still be using CR, but we're just talking about full field direct digital. And to do this, a computer has different image processing steps it must go through with the data collected. The captured signal must be digitized and then processed to create an image. The flat panel detectors in mammography are amorphous silicon and selenium, or direct and indirect detectors. Although still are both in use, it is recommended that you get a direct flat panel detector. This graph represents the direct detector. We're going to discuss both, but let's get back to image processing of the signal. We're taking an analog or continuous signal and digitizing it, put numbers to it, to be able to visualize and create a mammographic image to be displayed on a monitor. Once it is displayed upon the monitor, we need to be able to manipulate that image to get the best quality out of the data we've collected. The remnant radiation that is captured is stored on a flat panel active matrix array. The active matrix array is made up of rows and columns of DELs, or detector elements. They store the image data as an electric intensity that is corresponded to the intensity of the signal. So basically, we have a map of the intensities received and where they were received. That data is then correlated with a lookup table for the mammogram for the unit that you have. It is a computer paint-by-picture kind of thing. The cost of the detector is often represented by the size of the detector electronics. Obviously, the smaller the size of the detector electronics, the higher resolution you can get because you can put more detectors on the active matrix array. This means higher resolution, but at a greater cost. So let's take a look at the dynamic range, and that is the shades of gray that can be visualized in the signal that you've captured. Notice there are 3 levels of tissue that we want to show. One would be the chest wall, the other would be the skin line, and the third would be the fibroglandular tissue that is surrounded by fatty tissue that creates the breast. The number of recordings of shades of gray that we are capable of getting is from 300 to 1 to 10,000 to 1. So we have a wide dynamic range, a number of shades of gray that we need to map to create our image. Going back to our paint by number example, what we can look at is the fact that the number of paints would give us the dynamic range that we could utilize. Obviously, the more numbers of paint and the smaller the area being painted, the better the resolution and contrast. There are 2 distinct DR technologies available: a direct flat panel matrix array and an indirect flat panel matrix array to collect the data. We're going to take a look at both. We'll begin by looking at the direct matrix array, which is made up of selenium technology. The detector is made up of a thin film transistor coated with selenium. It will capture the energy directly into the area without having to utilize any other type of capture. The recorded intensities are captured and then they dissipate or discharge into the thin film transistor. Trapping causes a residual image called ghosting. The thicker the selenium, the more trapping occurs, so we keep it thin to reduce the DQE, or the amount of dose. DQE stands for Detector Quality Efficiency. Basically, with this detector, what we're doing is the negative electrons cancel the positive surface charge and thus produce variations in the surface charge that correspond to the intensity of the radiation captured, or the pattern of X-rays, or an image. Now we're going to look at the indirect flat panel, and that is basically taking and coating the active silicon matrix with a coating that fluoresces, or a screen that fluoresces, and the fluorescence is captured and converted into the electrical charge. Here we see the cesium iodide crystals that are grown from a vapor and then used to coat the active matrix array with an emulsion. These crystals act as little light pipes that fluoresce and change the radiation into energy to be transferred to the active matrix array. Notice that the active matrix array has not changed whether we're using direct or indirect. It is simply how we're converting the radiation to be able to be seen. The cesium iodide simply fluoresces like we do in fluoroscopy, capturing the energy, and the energy is then transferred to the thin film transistors where it is mapped and we can make an image. Just like in the active matrix array, in the direct capture, the indirect capture captures the fluorescence and changes that into an electronic intensity. The intensities match the radiation that they were created from, and therefore we are mapping the image. Here we have a small area of cesium iodide crystals, and we see that each crystal is about 5 microns in size. So how big is a micron? How much detail can we really get? Let's see how big a micron actually is. First, we'll take a cross-section of a human hair. The thickness of the human hair is approximately 100 microns, or 0.0039 of an inch. Let's compare the size of 1 micron to 1 pollen spore. The pollen spore is about 30 to 50 microns in size. If we compare it to a red blood cell, the red blood cell is about 7 microns in size. It becomes very apparent that the resolution using even the indirect capture is very good for mammography. Once the active matrix array has actually captured, it is called a charged plate, and we need to remember that the charges are equal to the intensity of the radiation received. Now, what do we need to do? We need to Digital mammography receptors usually have a linear response between pixel value and the radiation dose incident on the pixel or DEL over a very wide dynamic range, typically a factor of 10,000 to 1. The choice of what dose is required for digital mammography is therefore driven by the signal-to-noise ratio required for a diagnostic image rather than a specific radiation dose receptor. Different tissue densities require different amounts of signal to be demonstrated. On the detector element, or the DEL, it is the amount of that detector that is recording the intensities that determines the spatial resolution, as opposed to the size that it is sitting on. You can have a lot of area of dead space sitting around the active detector area. So the pixel size or DEL size is not a bit of magic, it is a choice by the vendor. Each vendor must decide on how much of each thin film transistor is providing capture as opposed to just being on the matrix. Digital resolution is measured in line pairs per millimeter. And when we talk about the DELs or the pixel sizes, they're measured in microns. So which size would take longer or more energy to fill? 4 big DELs or 1,000 little tiny ones? Obviously, it's easier to line up the 4 big DELs to begin with and fill them as opposed to the little ones. So when we talk about resolution and size and equivalency, what we're looking at is what intensity or amount of X-ray do we choose. The bottom line is that the more detail or the smaller the size of the DEL, it's going to take more radiation to get an image. So our speed relative is about 100 for 50 microns and about 800 speed for 200 microns. In digital, there is a difference between speed for mammography and speed and resolution for routine X-ray. You have to choose what matches. The last portion of this is about ancillary devices that you use with your equipment, and they can be everything from the different types of paddles you use to the types of markers to the types of identifiers that you may use to indicate different types of scars, etc. on the breast. As mammographers deal with this constantly, we're not going to spend a lot of in-depth time. We're just going to look at some of the basics on ancillary devices. Compression. A range of compression paddles are normally supplied with the digital mammography unit to cover different types of projections, or if you're doing fine needle aspirations, etc. Each of these is a sale to the vendor. I'm sorry if I sound a little cynical, but everybody has their own special, this is better. When in reality, you need to look at what you need, why you need it, and what is best for your patient. You should not only look at ancillary devices as to how they're going to impact a patient, but how are they going to impact you with your daily work with the patient in positioning. I know patients hate compression and they also fear it. when you look at your machine, the maximum pressure it should be able to apply is 200 newtons. 111 newtons is 25 pounds, and 200 newtons is 45 pounds. As skilled mammographers and radiographers, I'm sure you're all aware of the thickness and tissue composition, how it relates to exposure. And we know that compression of the tissues allows us to get better quality images and better resolution with less exposure to the patient. Some of the older paddles that are around, or compression paddles, are the flat, rigid paddles. Today we try to have the paddle be able to tilt and conform to the breast itself while still performing the compression and holding the breast still. And here we see an example of the tilting flat paddle. It allows rotation against a spring resistance so that the compression of the chest wall edge of the plate will be higher than the nipple side. The advantages are claimed to be that the design holds the breast in place more firmly. Here we see the sliding compression plate, and this plate is suitable for imaging smaller breasts where the full area of the image receptor is not required. And of course we have the spot compression plate where we're looking for a specific area that we want to compress. We also have our magnification set up. The magnification gives us 1.5 to 2 times actually of magnification, and it is increased effective resolution of the image receptor by the magnification factor. The small focal spot size is used, and we reduce the scatter radiation through the air gap technique. Here's a close-up of the spot compression plate. You can have either a cylindrical area or you can have a rounded area. And to the left we can see the setup for the magnification view utilizing the spot compression plate. And as we discussed, we can have a biopsy compression plate as one of the ancillary devices as well. After seeing all of the documentation on how the components work, how do you compare your mammography equipment against other mammography equipment, and what do you think you'll look for in the future? Thanks for your time. I appreciate it very much, and we'll have more mammography presentations coming up, including breast cancer in men, transgender mammography, and some anatomy and physiology. Thanks again. Bye now. This is Mark Struthers.